So this is sort of this is my second time talking about this, and we've had, so this is kind of, I guess I was told, supposed to be sort of an update, so I'll make it that way as much as possible, but I can't do anything before I talk about the people working on this. So this is not just myself, it's Professor Yves Rubin in chemistry and Mitchell Spearin, and then a bunch of students, and so instead of just kind of reading them off, and there's more, I'll have pictures of the ones in certain areas that they're working. And then the support started from what was called the Noble Fund, now the Elman Family Innovation Fund. The next sponsorship that we had was from the California Energy Commission. And now we have 2 US Department of Energy grants. All of those last 3 are for field demonstrations of what I'm going to tell you about that's happening in the lab here. So they're all young. We'll be out in the field later this summer, and we'll be actually shooting sunlight at things about a year from now. But again, thanks to CNSI and Magnify. These are fantastic programs. I brag about CNSI all the time because I have a lot of friends back at Purdue who were from the Burke Nanotechnology Center. Purdue hired me to help occupy or plan and occupy that. And so I know especially how difficult it is to run an operation like this. It's not simple at all, and to keep everything afloat, and I greatly appreciate the support. So my outline is here, but you're going to have to forgive me because I didn't read my email very well, I think. I thought that this was a normal academic seminar, so I planned it for 50 minutes, and they said 20, 25. And so there's going to be some moments where I'm going to sound like a chipmunk. Just kind of go through things really quickly. But I don't want to go too far or too deep before I kind of talk about at least why hydrogen and graphite are important. I think there's enough popular press to understand that hydrogen is happening. But for those of us who are old enough, we also remember 20 years ago when the hydrogen economy was supposed to be hitting and it didn't happen. And so that doesn't make me a skeptic about it, hardly. I'm working on it. But it does give a sense of perspective and kind of the importance of being circumspect about projections on alternative fuels especially. But the graphite part, a lot of people don't know this, many do, but graphite is a key constituent for energy storage that could come from hydrogen energy, right? So graphite is the largest material by mass in a lithium-ion battery. It's the anode. And so it's, not only, right, is there a large market for it today, but it's projected to explode. Actually, the battery graphite has not yet even surpassed the use of graphite in steel manufacturing. So in electric arc furnaces, they're the electrodes. That's still the at least by, I think, value, that's the largest component of the graphite market. But they're growing. It's getting bigger and bigger. So these are important things to talk about, important materials. How do we make hydrogen today? So if you bought hydrogen on the open market today, you'd probably get it with steam methane reforming. They could make it for about $1. I was talking to a VC up in Silicon Valley yesterday. They said it's 89 cents today. But that's without carbon capture. Once you add carbon capture to that, you're adding at least $1. Methane pyrolysis which is what I'll talk about, is $2 to $3 typically. So it's not competitive enough to supplant really any of that SMR. And then what most people hear about today in research on hydrogen, it's the last one. That's hydrogen electrolysis. They color code it, right? Green hydrogen, the electricity comes from renewables, all that. The most important symbol on this chart is the greater than sign there. I would just tell you that. I know a few people working in hydrogen, maybe there's some in hydrogen electrolysis, and I could tell you they're going to be really happy if they can get it under $10 a kilogram. They're going to be super stoked about that. And so it's not looking like a great pathway, but obviously we have great hope. Also, to give you context on that, a kilogram of hydrogen gives you about the same energy content as a gallon of gas. So you can compare those numbers to just the price of gas. So why is methane pyrolysis not all that common today? There's all kinds of issues with it, but mainly it's this picture. It just gets so dirty. You're making usually amorphous carbon. There's a company in Santa Barbara that's making hydrogen this way, and they're burying it's not even worth shipping the carbon black, right? There is a market for carbon black. It's in your tires, it's in some cosmetics and some paints, but it's not even worth them shipping it. They just bury it in the ground, and that's it. That's where the carbon goes, and they sell the hydrogen. This is a perfunctory slide for if there's solar thermal experts in the audience. There are papers here. I could give you my slides. I'm not going to go through this except to say there's been some really clever things done with trying to capture the sun in a concentrator and then put that sunlight into a reactor, including cracking methane, but also many other things. There's never been anything that really took off. We had a visiting faculty member here from ETH Zurich 5 years ago, Aldo Steinfeld. He started a company 20 years ago that was going to try to do this, or that did try to do it, and it never really went anywhere. And I could explain reasons for that, but it's enough different than ours. And the bottom line is they were never making graphite. They were making, again, hydrogen and carbon black and throwing away the carbon black. All right, so I believe that one of the dying arts in academia is instrument building. And so I'm going to bore you with some slides about instrument building. We have built an instrument in this building from scratch. Almost everything in it was the least common denominator component that we put together. We didn't buy much of anything like assembled. We could have some of the things. But so we have a light box. And that light box is in 4537C. We have another one as well that we're standing up. But these things we built with our hands. It's 10 kilowatts electrical. We have really made people's lives difficult in this building because we draw a lot of power. I will just tell you that. I thank you for your patience with us. There's still other issues. There's gremlins in the walls that I work with Adam Steeg about. But anyway, so we built this thing. So essentially it's an ellipsoidal concentrator. So it's a truncated ellipsoid. That's the thing on the left. There's something blue you see those cables that are reflecting back to the camera. But then there's a bulb at one focal point. It's a xenon arc lamp bulb. It shoots into the reflector, and then that reflector concentrates it back in our reactor. And I'll show you some more pictures of how this actually works. From the outside, you see that the left side shows the aperture. We actually have a dowser, like a mechanical dowser on this. The components here, if you were go to build it yourself, DIY, it's actually, this comes from concert spotlights. Concert spotlight technology is what this is. The optics are a little bit different, but that's what we buy, the dowser and things like that. That's where we get it. And then in the right figure, that's one of our reactors. That's what we call the horizontal configuration. So the light shoots into a window that is right here. So the light's coming in this way, and our reactor is in the middle, our reaction zone. And so I had lots more slides to tell you about, but one of the things that we can do is we could actually do high temperature material characterization. In this case, we are measuring the heat flux. So we have to calibrate. We built this thing ourselves, so we have to calibrate the source. And so we basically built our own radiometer. The bulbs fade over time, and so we have to do periodic recalibrations on this. And there's nobody else that's going to do it for us. You might say, I'll put a power meter there, put an optical power meter. This is 4,000 suns at the peak. Any optical power meter that you would want. I mean, you could put neutral density filters in, but it would fry. And so we have made our own. We basically built our own instrument. Then what we can also do, and we can control our power, our light power coming out. We put it into a sinusoidal wave, and we can actually measure thermal properties at high temperatures by looking at the amplitude change as a function of radius and the phase lag as a function of radius. So we can do these things. There's some beautiful math that sits behind that. But we can do this at very high temperatures, which has always been a challenge for really anything. And that's why we're talking about what Mona is doing. We're going to be using this for some electronics testing. So for basically probe station kind of things. All right, so probably what you came for. This is a schematic of what it looks like. And the most important thing is that and the difference between what anyone else had done before is that instead of kind of having a volumetric reaction zone where you might seed some particles that were flying around and they would absorb the light, we actually have a porous web here, and that absorbs the light, and we flow our reactants through it, okay? And the reaction happens on the web as the material flows through. There's a lot of advantages to that. First of all, there's no intermediary. The thing that's the hottest is also the place where the reaction is happening. I don't have to transfer the heat. I also do not have this problem with boundary layers. When you flow a fluid through a porous medium, you basically have broken up the boundary layers. And so a lot of that diffusion problem that you have in reactors goes away to a great extent. And then on the back side, you're going to see some images of a thermal camera that we have. And I'll also show some data on how we measure the product stream, the species. But that's really Mitchell Spearin's work. I'll highlight Mitchell and Yves a little bit later on, but I don't do justice to their work, and so I'll mention it and let them fill in the blanks. That is really complex and cool, and it took a lot of time to build. If that's what you take away from this slide, you got the point, right? So this was Mostafa and Abdallah mainly. I showed pictures of them. They both graduated with PhDs in late 22. But this was all built. If you go day one of the pandemic, there was nothing there. And by day 400 of the pandemic, we were putting things out. It took over a year to do it, but it's all built by hand. And you can go see it anytime. It's in, like I said, one floor down here. I'm a heat transfer person by training, and so this is like the greatest heat transfer problem ever, I think, maybe, right? Because what do I have? I've got radiation, obviously, from the light, but also re-radiation out. I have heat conduction in this porous web. It's a complicated heat conduction problem. I have fluid flow, porous media flow, right? And then I have reaction, thermochemistry. All of these things are happening. So somebody was looking at it. I said this is so it's got everything. And then, of course, Jeff Eldridge in our department said it doesn't have turbulence. And yeah, okay, so it has everything except turbulence. It even has phase change, right? Because we're depositing a solid from the gas phase. So lots and lots of, so at least multi-phase flow. So it's a lot of fun, very complicated problem. I'm only going to give you highlights. In this case, we weren't running it at full strength. So at the peak, we had 3,400 suns. So that's 3.4 megawatts per square meter. We're putting out, in that case, it was almost 2 kilowatts total. And we're getting to temperatures, this is Kelvin, in the peak, about 1,600 Kelvin. Okay, but it rapidly drops off, right? So the big problem, we thought this was a big problem. I'll show you how we made lemonade out of that lemon later. But it drops off really steeply because it's a bulb, it's a point source, right? And so if you're going to do just linear optics on it, then the image is also going to be very peaky, and that's what we find. So we have this big temperature range when we flow this material through, and you can kind of see a bullseye. When we first saw this, right? This would be about 2.5 years ago. It was gray in the middle, and we thought, what's oxidizing the graphite, right? And then we looked at it and we said, oh, wait a second. Graphite's silvery. So we did not expect graphite, I will tell you. No one that's an expert in this expected graphite. And we've been accused of hiding a catalyst in here somewhere. There is no catalyst, right? So the first couple of reviewers of our papers were like, reject. They didn't tell us what the catalyst is. You know what we hadn't done? We had said it, but we hadn't hit them over the head that there is no catalyst, right? So that's the big surprise. But this little gray region in the middle, that's our canary in the coal mine when we see that. Well, maybe that's the wrong metaphor, but that's our indicator, our measure of goodness. We know that when we see gray, in the center that we've got graphite. And then, of course, we measure it. But the other thing that's really neat about this is it's very, very fast responding. And people who have tried to do solar in the field, and there's a lot of graveyards for concentrated solar in the deserts of the United States and around the world. This is a really fast responding system, and that matters because one of the issues is just clouds and haze and other things. Minute to minute variability in the insolation is important, and you need to be able to engineer around that. And not very many places have, or not very many technologies have, but this can. It responds in a matter of seconds. But what do we grow? So we started out with this felt. I should have brought props, but I have plenty down in the lab. The felt started with this. It was carbon fibers, right? So this is how it started, 10 micron diameter. And after, this is 20 minutes of growth in the center, at the hottest spot. The diameter is 100 microns, and this was 20 minutes of growth. That's all. I come from back in a prior academic career life, part of my life, I tried to grow diamond. So if you can grow diamond at 1 micron per hour, that's not bad. If you can get to 10, it's awesome. So this graphite, it's not diamond, but this graphite is growing at over 100 microns per hour, well over 100. Right, which is, so we have not been able to find, I've put this up in enough external seminars, you never know if you're going to miss a paper here or there from the old days. But the closest non-catalyzed graphite synthesis by CVD that we can find is 100 times slower. That's the fastest we can find. So this is 100 times faster graphite growth than we can find. But if you know of something else, you let me know. Yeah.
Is the felt somehow nucleating graphite deposition?
It's certainly capturing it, but it is. But there's still an open question about the catalytic behavior that's there. But I could tell you, we put in all kinds of inorganic fibers. It's the same thing, the same growth rates, the same. There's nothing that we can tell that's different from that. So that's a great question. The carbon quality. This is one example. But what we have, so we have a very good profile, especially in the hottest parts, right? So the G peak in the Raman is 7 times or something like that higher than the D peak. We can get even better than that. We see high crystallinity in the XRD. So these are all really good pointers toward high quality graphite. And then I just wanted to also, this slide was inspired by my last seminar to this group. Because somebody said, people have been pyrolyzing methane for a lot of times, and so, and making graphitic-like materials out of it, what's the big deal? This is the big deal. So if you go in the literature and you look, this is catalyzed. But they will call this graphitic carbon, that stuff on the left. It's fuzzy. It surely has nanograins of graphite, right? Because you can see the G peak in their Raman, which is kind of a messy Raman, but still. And this is ours, right? There's a huge difference between those things just aesthetically, but also look at the G peak here. I mean, especially when we added a little bit of hydrogen, there's no D peak, that's the defect peak in the Raman, and this huge, narrow graphitic peak, and it's cylindrically layered, which is also something that people haven't seen before. I used to work in carbon nanotubes, and it's like, this is like the mother of all carbon nanotubes, except it's not quite open in the middle. We still have the original fiber there. So, but it's just beautiful. It has lots of potential for mechanics and heat transfer in addition to electrochemical storage. One of the things I also has been added recently, so people say, well, so what's the big deal, right? You can make graphite, you can buy synthetic graphite on the market. What is that process? So the process to make synthetic graphite today is the one on the left. You take petroleum coke from a refinery, and refineries aren't going to be, there's not going to be as many of them for as long, maybe, if people, if we do well on renewable energy. But in any case, that's where they get it today. And you bake it in a programmed temperature profile up to 3,000 degrees C. But look at the time scale. Days, right? It takes days to make synthetic graphite. Our process, the residence time of the methane in our reaction zone is 10 to 100 milliseconds. Milliseconds, right? The whole growth time to make the thing that you see here is 20 minutes. Right? So it's just a huge, orders of magnitude faster process. We're still trying to understand all of this. And of course, that on the left is basically a solid heat treatment process. It's not a gas phase reaction, but the time is the same. The clocks are the same, right? So that's a big deal. I think I'm going to skip this slide because I'm going too fast. But we've now, of course, since we last talked, we look at the effects of flow rate. There's lots of scholarship that we're putting up there. One of the things that we did notice is that over a longer period, past 20 minutes, the outlet stream product, right, started to revert back to more methane, less hydrogen, meaning less reaction. And what we found is that the fibers coalesce, right, and they just block the flow. It was growing too fast, right? That's the problem. It's a good problem to have, because then what we did, and this just came out at the end of last year, right? We just put the web on a roll-to-roll system, and you can see that after 20 minutes in stationary, a certain flow rate, it drops off. As soon as we start rolling, we get fresh cloth back in there, it picks up. Then we did it again, stationary, but at a higher flow rate. And when we roll, we can recover that. So when we roll, so now we have roll-to-roll processes that we've proven out in the lab, and that we're designing into our field units. That's very mechanical engineering of me, right? So Bob McCloskey's back there. He's probably telling me that he can control that with some kind of lemma. And I bet he can. All right, so
Take your time. We've got time.
We've got time? Okay, good.
Right.
You could tell I'm rushing a little bit, but I wanted.
No problem.
So now this is going to be more of a, I don't know, kind of a rump session, just telling you what we're doing lately in various ways, and it's a lot of fun. So Eve and Mitchell, they're working on reaction chemistry, right? And they're fantastic. And I'll have a couple slides on their things. But what really trying to understand the photocatalytic behavior here is how much is direct photolysis happening versus sort of indirect excited state or non-equilibrium thermodynamics happening. We want to maximize yields, so we use some data science, right? I hesitate to say any other words, any other buzzwords about that, but it's actually working. I'll show you a slide. It's pretty neat. And then minimizing the cost, scaling up the process. These are the things that are on our minds today, right? And so Yves and Julia, his PhD student, they're looking at different chemical precursors. We're kind of zapping some of these precursors to see if we can make graphene nanoribbons. If we have those in the mix, will that change the ultimate morphology? Will it change our stacking of our graphene? All kinds of things that are more fundamental, but still very much aligned with the general topics of the research. And so it's a very experimental synthetic chemistry kind of approach with precursors. And she's also helped in a number of other ways with looking at the products and analyzing the graphite products that we make. One of the things that we are kind of, slowly working our way into is what's happening in between the beginning and the end of the reaction, right? It's not like you just chop off carbon atoms and they self-assemble into graphite, right? There's these things, intermediates called polycyclic aromatic hydrocarbons, for example. Pyrene is the most dominant one, we think. But they have absorption lines in the near UV and visible, depending on how big they are. And are those capturing some of this light and actually kind of turbocharging the kinetics? Because we have to be looking for reasons why the reaction's happening so fast, right? It's another one of those good problems to have, but there's a lot of good science that goes behind that. Yijun was my PhD student and postdoc. She started to do some DFT type calculations on this, and now we're setting up experiments. So that's Mitchell and Barathon. And so I told you that we had gas phase laser diagnostics in the product stream. Mitchell and Barathon are now setting up, and this is down here. That's this module at the end, and we're basically moving that to the reaction zone. So we have to build an entirely new reactor. And we're going to be hunting for polycyclic aromatic hydrocarbons. We'll be hunting for, just maybe methane and using temperature. So using the diagnostics to measure temperature. It's very hard to measure temperature on the front side of this problem because you have thousands of suns hitting, and so putting instruments there, there's really no optical way to get to it, but from the side you can get to it, and that's what Mitchell is working on, and Barathon. Interesting thing here, this was what the last thing Mostafa did, still not published, is that if you look at the front side, so I just told you it's hard to measure the front side temperature, but Mostafa did once. I think he broke something along the way, but he did. And so over time, this is our standard 20-minute period, the backside temperature, that's the side that's not illuminated, starts out, still hot, but not quite as hot. And the front side temperature is really hot, and then they merge together because we're growing graphite on the substrate. Its thermal conductivity is getting a lot better over time, right? So that's one reason here. But then we started to look at this, the question of photochemistry. So you have to look at this, and I'll have another slide of this. We put a shadow mask in front of the light source, so just with a hole and some struts on it. And then we looked at the growth rate in the shadowed region and the directly irradiated region, and you see this big, right, this big change. And so we looked at this and said, that's photolysis, right? Must be photolysis. And then we saw things like this, right? He just got lucky in the SEM, and he actually saw a place where he was going from the illuminated spot region to the unilluminated region, kind of just followed that fiber diameter down, which I thought was that's sort of a hero experiment kind of result. But we've done more looking at this. So that graph on the left is the same. Now, Hengry, my PhD student, has picked this up. Same graph on the left. In the shadowed region under the center circle there, you get a growth rate, but it's much lower. And then as soon as you get to the exposed region, you get this direct irradiation. And so Hengry is working on the heat transfer model that tells us what that front side temperature is. This is what he predicts now, right? So he has that. And so now we're looking at this saying, not so sure there's much photolysis here because the surface temperature in the shadowed region is the same as the surface temperature that's circled here in the exposed region, and their growth rates actually look like they line up. So we're not sure. It's a mystery. If people in the audience here want to have ideas on how we can chase this down, I'd love to collaborate on that. And Mitchell and Eve are also pondering it and thinking of ways to do it. But other than that, you've seen this figure. Hengry's working on battery electrodes. Ben is a new PhD student that is working on, I told you that there's some really interesting mechanics, right? So what happens when you have this cylindrical graphite at 100 micron size diameter? What does that mean for mechanics and carbon fiber composites? So that's what Ben is working on. He's in, the beginning of his second year, I guess, in the PhD program. Closing out, so we have made graphene, and Abdallah did that for his PhD. He graduated in December 22, but then he came back for a short postdoc, and then he had to go back to UAE to start his faculty job. But he built this, and so this is the data science kind of thing. So there's all kinds of different factors that affect the growth process, right? You see them here. How much light I put in, pressure, time, gas, temperature. All of these things affect the growth. And in his case, he was studying the effect on graphene growth, on copper, not the graphite that you saw before. But this is what I want to emphasize. So he did a Bayesian optimization process of his experimental design. And I know that there's just a lot of data on here, but I want to explain the main things. So what he did was he said, I'm going to start with instead of designing my experimental campaign at the beginning and then just executing it, he had a series of tests, and you can see that they're very scattered. So in this case, our measure of goodness is the D to G Raman ratio. The lower the better, and then versus that in an experiment. So that he designed a first set of experiments, and then he went into this Bayesian optimization routine and said, design me another set that maximizes my information function. He did that Now the red curves get a little bit closer to this ideal line. He did that a couple more times, and by the time he's at series 6 of his experiments, he's spot on. So we have a surrogate model. This is not a physics-based model, but we have a surrogate model that basically tells us how all of those other factors affect the quality of the product that we have, right? And he did this. I mean, I know there's a lot of points. Abdallah, you probably heard him snoring a lot if you were walking the hallways because he was in the lab. But to get that same result with just like a full factorial design, it would have been 10 times more experiments. It looks like a lot, but it could have been, you know, an absurd amount of experiments. So field scale up. So what we're doing, so we have 3 projects, 2 sites. We have a project from CEC that uses a 10 or 11 kilowatt dish. Okay, so that dish exists, and SoCalGas is kind of the manager of it. And we're using it for converting biogas to hydrogen. That's the target. Is hydrogen is the target, biogas is the only allowed source for that one. And then we have a DOE NETL, so that's the National Energy Technology Lab. That's the Pittsburgh, West Virginia folks. The old clean coal part of DOE. I finally got money from them after trying for like 20 years. So this is in Arizona. This is going to be a 40 kilowatt dish. That's the actual dish that it is. It's not the receiver, right? And so this is in a place called, it should be called Casa Grande, but if you go to Arizona, they call it Casa Grande. So yeah, and it's strategically located for me because right here underneath Guadalupe, I have grand twins, and I'll soon have a second set of grand twins right there. So I will say that was not a random choice, but there's lots of good sun here. And then the third one is so this one is to take natural gas and turn it into hydrogen. And then the third project, which is led by the company, but UCLA is a part of it, is to use that dish, which is again owned and operated by SoCalGas, and focus on making the graphite for batteries. So those are our 3 field demonstration projects that we have going on. And we're looking at many other places around the desert southwest, but this is the place to be. I mean, actually, on Earth, our sun here in the desert southwest is better than it is in the Middle East. You know why? Sandstorms. There's too much sand in the air, dust in the air, so the actual direct normal irradiance in the Middle East on average over the years is not as good as we have here, even though they have fewer clouds. So again, here's Ben and I. We were lucky enough to be selected to go to the COP28 UN Climate Change Conference last November, December. It was very interesting. I can tell you that if I had wanted to set up my company in Dubai, I would have been all set because that's who the people are that we met. I'm not setting up in Dubai. Maybe someday we'll do something there, but that's it. Anyway, thanks. I'm happy to take questions.